Okay, so we are in chapter 7, so 7.1, rational expressions. So I have some typed up notes here. A rational expression is an expression written in fraction form. So essentially, rational just means fraction. So rational means fractional, all right? So anything P over Q, so some fraction. So we have rules for rational expressions, and this is just important things that you're supposed to understand, and that's just going to help you make sure you simplify your problems correctly. So one thing is the negative should be applied to the numerator or to the center, right? So remember that a fraction simplified should never have the negative value remaining in the denominator. So if you see from these two examples, if you have 2 over negative 7, the simplified answer should be negative 2 over 7, or you write the negative directly in the center. All right. If you have the expression, because remember this is algebra, so we're going to be dealing with algebraic rational expressions, which means fractions that contain variable components. So if we had this problem here, x plus 2 over negative x, you could not leave that as a simplified answer. It would be incorrect. So the simplified answer would have to apply the negative to the numerator and then have it like that so that you could then distribute. So this is a correct answer, or this is a correct answer, or this is a correct answer. Okay? All right, so all of those would be considered correct. So you just have to make sure that you understand that the negative should never be left in the denominator for a fraction. All right, the second part of rational expressions, the denominator can never equal 0. 0 in a denominator is undefined. So you may not have a rational expression that has any values which would make the denominator equal to 0. So essentially this second rule about rational expressions, it comes into play for us because we're dealing with algebraic rational expressions, which means there are variables which are unknown values that could end up in the denominator. And so if we have a problem that has a variable in the denominator, we have to make an account for what that x or what that variable can never be equal to. Okay? So the example we have here, I have x over x plus 3. Example 1. Find the values that would make the rational expression undefined. So here's what you have to do. Remember, you have to make sure that you understand the directions, which is vocabulary, so that you can teach your brain what to do when you see those directions. So the directions say, find the values that would make the expression undefined. Find the values that would make the expression undefined. So in order to do that, everything is about a process, steps. So in order to do that, we have to set the denominator equal to 0, and then we solve for the variable. So anytime you have a rational expression and your instructions are telling you to identify values that would make it undefined, that is referencing the denominator only. Because the only thing that can create an undefined expression is if you have a 0 in the denominator. So if I have x over x plus 3, and I want to identify what values of x would make it undefined, what are we saying? We are saying, what is the value of x in this denominator that would create a 0 at the bottom? Okay, so the way that we do it, you can look at it and understand it. What plus 3 would give a 0? And if you can't think of it in that way, you just set the equation equal to 0, and you will be able to identify it that way. So we solve for x. So our minus 3 on both sides. So x is equal to negative 3. So what does that mean? That means that negative 3 would cause the value to be undefined. So what we are excluding from the domain is one word they use, domain, or the value or values that make the expression undefined would be negative 3. So x can never equal -3, because if x equals -3, it would make it undefined. And that's all you have to do. You just have to be able to look at the rational expression and identify any value that would make it undefined. So you set the denominator equal to 0 and solve for x. And that's going to be one problem type for rational expressions, identifying what values that would make the expression undefined. Okay? All right, so here we are going to do 7.1 examples. So the instructions say find any number for which each rational expression is undefined. So we have two components on these problems. First, we have to identify any value that would make it undefined. The second part is then we're going to simplify. So what we've already done an example of is defining values that would make the expression undefined. So let's look at x squared minus 16 over x plus 4. If we want to identify the values that would make it undefined, we would simply take the denominator, set it equal to 0, and solve. So x should never equal -4. That's all you're doing. Find the number for which each expression is undefined. So that one would be -4. And that's it. Okay? So like if we do number 2 over x plus 7 squared, so that would be x plus 7 equals 0, x equals -7. So that would be -7, and that's it. So you just identifying the values that x should never be equal to. And then if we look at the third one, we would set that denominator equal to 0. All right, so we have to solve this. How do we solve this? Okay, so here we set it equal to 0. Now, this is where, and this is a big part of chapter 7, you have to know how to factor. You have to know how to solve by factoring, okay? And this is all chapter 6. So if you actually understood chapter 6, chapter 7 is going to essentially be extremely easy. So a squared minus 25 equals 0. I would factor those, which would be a minus 5, a plus 5. And I set each factor equal to 0. So a should never be 5 or -5, right? Because I add 5 to both sides. I subtract 5 from both sides. So a can never be 5 or -5. So those are the values that would make each expression undefined for numbers 1, 2, and 3, right? So anytime they're asking you about what would make it undefined, it's all about the denominator. Set it equal to 0, solve for x, or solve for your variable. All right, then we go into our second part of 7.1, which is simplifying rational expressions. So let's look at that. All right, so 7.1 is rational expressions. So now we're on the second part, which is about simplifying rational expressions. So let's go through the definition of rational. Rational means fractional. So there's a fraction review before you start chapter 7, which helps put you in the mindset of basic fractions before you get to the algebraic part, which is rational expressions, right? So when we just have a regular fraction, let's say we have 4/8, we want to simplify that. Well, how do I know it's not simplified already? So the definition of simplifying a fraction or simplifying a rational expression is that the numerator and the denominator only have a 1 in common. So the numerator and the denominator do not share a factor other than 1. That's what it means if something is simplified. That's a basic fraction definition. So 4 over 8 is not reduced because 4 and 8 share a common factor other than a 1. So what we learned is we learned something called prime factorization, or you can just know the largest common factor, the greatest common factor for each component. So if you were to break each value up into prime factors, which is, we used to use a prime factor tree, right? Then you could cancel. So when everything cancels in the numerator, you hold that space with a 1, remember? And then the denominator would just be 1 over 2. Now, also 4 over 8, if you already know that they both share a 4, you could just divide out by that 4 at the top and the bottom. But it's important for us to understand the prime factor way because we are dealing with rational expressions that are going to have variable components in them. And so we are going to need to make sure we know how to factor things down as much as possible so that we can then cancel out the common factors. Okay? So let's look at this first example. So x squared minus 16 over x plus 4. So when we were looking at the 4 over 8, we know our multiplication tables. So you don't have to break it down using the prime factors the way I did it, breaking it down into 2 and 2 and then 8 and all of that. Because if you know that 4 can go into 8, then you can break it down and reduce it that way. But when we have expressions that contain variable components, you don't know how to break that down. You don't know what the common factor is from x minus 16 to an x plus 4 just by looking at it. Factors are things that multiply. So no, you cannot just do 16 divided by 4. It does not work out that way. These are each one of these is its own factor. So factors are things multiplied. So x squared minus 16 over x plus 4. So x plus 4 is its own factor. So x plus 4 cannot factor. So x plus 4 is where I put my parentheses around because that is the factor. X squared minus 16 can actually factor further. So I'm going to factor that because what is it? It is the difference of two perfect squares. So it factors into x plus 4 times x minus 4. In the bottom is x plus 4. So I did my two steps. I factored out the numerator and the denominator, or I factored the numerator and the denominator if possible. So you factor where you can. So I looked at my numerator, it was able to factor. My denominator could not factor, so I just put it in parentheses because it is its own factor. So when I look at this, the second step says this is cancel. Cancel out like factors. So just like we did on this problem over here, you cancel 1 to 1, right? That is how we cancel. That is a reducing of a fraction. This is the same thing, except now they are algebraic expressions. They're algebraic fractions. So you cancel out the like factors. It's still the same. Your factors just won't necessarily be numbers all the time. They will be binomials or have variable components in them. So when we look at this, x plus 4 and x plus 4 would cancel each other out. All that's left is x minus 4 over a 1, essentially, which is just x minus 4. Okay? And that's it. So that is how we simplify rational expressions. Simplifying rational expressions is just you factoring where you can factor, and then you cancel out like factors. And that's it. All right, so let's look at number 2. X squared minus 49 over x plus 7 squared. So we're going to write this out and write everybody in its factored form. So x squared minus 49. So my recommendation is to really kind of split your paper so that you can factor your stuff on the side, which is like your scratch work, and then bring your factors back into your problem. And then x plus 7 squared, that means x plus 7 times x plus 7. So you want to write that out, and then we see what can cancel. Well, an x plus 7 can cancel with an x plus 7. So what does that leave us with? X minus 7 over x plus 7. It's very important for you to understand you cannot cancel an x over an x here, because this is not an x. This is an x minus 7 and an x plus 7. You can only cancel factors, meaning things that are being multiplied to other things. So this is your final answer, x minus 7 over x plus 7. And that will be it. The problem is over. All right, let's look at number 3. 5a squared plus 25a over a squared minus 25. So again, I recommend that you break up your sheet and do a little line separating your scratch work from the problem. So I'm a factor for 5a squared plus 25a. So I got to factor that first. So I have a GCF present. So then a plus 5. And then for the denominator, a squared minus 25 is the difference of two perfect squares. So a plus 5 and a minus 5. I'm telling you right now, if you don't know how to factor, you will struggle in chapter 7. You have to know how to factor in order to do this chapter. So if you didn't get factoring, this is another opportunity for you to practice it, to get it, so that you can get to this chapter. So once you've factored, you're going to rewrite your factors to replace your original problem. Because what are we doing? We are trying to reduce to lowest terms, essentially. That's what simplifying a rational expression means. It means just reduce it to lowest terms. Lowest terms means you have taken out all common factors in the numerator and the denominator. So we have factored this down. Now I'm looking at it in its factored state. Do I have like factors? Yes, I do. I have a plus 5 over an a plus 5, which cancel each other out. What does that leave me with? Well, in the numerator, I'm just left with 5a. And in the bottom, I'm left with a minus 5. They do not cancel. You would have to have another a minus 5 to cancel, or you would have to have a 5a at the bottom to cancel. So 5a over a minus 5 will be your final answer. And you don't have to have it in parentheses. I'm keeping it in parentheses just so you can understand you can't cancel an a with the a. That would not work. All right? All right, let's do the next row. So number 4, we have x squared plus 5x minus 36 over 3x squared plus 27x. So again, on the side of my paper, I'm going to do my scratch work. So I have to factor x squared plus 5x minus 36. So you go through your factoring process. Factors of 36, that'll give me a 5. 9 and 4. So x plus 9, x minus 4. So you should have as much space as you need to do your factoring process, however you do your factoring process. And then my denominator has a GCF of 3x. So I get x plus 9. So nothing can factor. They can't factor anymore. So when I write it over, I'm going to write everybody in their factored form now so that I can see what can cancel, right? Because in the original form, x squared plus 5x minus 36 over 3x squared plus 27x means nothing to you. I don't know if they got common factors. I can't see that in that form. So I factor it so that I can see if they have common factors. This is how we have evolved from regular numbers. If you give me 4 over 8, because I know what multiplies to create a 4 and an 8, I know they have common factors. I don't know what creates x squared plus 5x minus 36 just from looking at it at the top of my head. So I have to break it down so I can see it in its factored form, and then I can determine, oh, they do have common factors. They both have an x plus 9. I wouldn't have known that if I didn't break it down. So now I have x minus 4 over 3x, and I'm finished with this problem. That's it. You either can factor or you can't. If you can factor, then chapter 7 will be a breeze. If you cannot factor, chapter 7 is going to be more work for you. But all this is factoring, canceling out like factors, period. Okay, next one. All right, so we have 6x squared plus x minus 2, 6x squared minus 5x plus 1. So I'm going to just do my scratch work over here. So I have 6x squared plus x minus 2. So I have to do a times c. So negative 12. So I need factors of 12 that'll give me a 1. So I'm going to go with 4 and 3. Plus 4x minus 3x minus 2. 3x plus 2 minus 1. 3x plus 2. So 3x plus 2 times 2x minus 1. So that's my first one, and then I do my denominator, 6x squared minus 5x plus 1. So a times c is a 6. Factors of 6, that'll give me a 5. I need a negative 5 and a positive 6. So if I choose 1 and 6, that gives me negative 5. But if I multiply those, it would give me a negative 6. So I'm going to have to use 3 and 2. So 6x squared minus 3x minus 2x plus 1, split it. I get 3x, 2x minus 1, 2x minus 1. So 2x minus 1 times 3x minus 1. So I have my my factors for numerator and the denominator. So this top, 3x plus 2 times 2x minus 1. And then the bottom, 2x minus 1 times 3x minus 1. So when I look at them in factored form, my 2x minus 1s can cancel. So that leaves me left with a 3x plus 2 over 3x minus 1. And that would be the final answer. No, you cannot cancel 3x and 3x because they are not factors. They belong with the plus 2 and the minus 1. Factors mean things that are being multiplied to other things. So because the 3x is adding to the 2, the factor is the 3x plus 2. The factor is the 3x minus 1. Therefore, the 3x's cannot cancel each other out. Okay? All right, next one. So 49 minus y squared over y minus 7. So, first of all, we would need to rewrite this problem because it's not in descending order. So, basically, I'm trying to factor. So I have to factor the numerator, factor the denominator. The denominator can't factor. It's y minus 7. So I just put parentheses around it because it's as far as it can go. The negative y squared plus 49, I'm going to put that on the side. And my pencil's going to die soon, so hopefully I can finish this problem. So if I factor out negative 1, remember you should always factor out a negative if the leading coefficient is negative. So when I factor out the negative 1, then it allows me to get the difference of two perfect squares. So I'm looking at negative 1 times y plus 7 times y minus 7 all over y minus 7. So all I did was take my numerator and use my rules of factoring to factor it. So then when I look to see if I can cancel, the y minus 7s can cancel out. So what does that leave me with? Negative 1 times y plus 7. Or if you want to distribute it back, you can. Either answer would be correct. Okay? And that is 7.1. I'll do a second video for the last 3.